In this video, we're going to look at how to design a reinforced concrete beam for Flexure using S-Line. For a bit of a description here, we have an 8 meter long simply supported beam that's 500 millimeters deep by 400 millimeters wide. We have 5 20M bars and 10M ties. And we're going to assume a 40 millimeter cover, and the concrete material strength will be 30 MPa, and the steel yielding strength will be 400 MPa. We're going to run this through S-Line in just a second and ensure that our capacities match those from hand calculations. In terms of our loading, we have a dead load of 5 kilonewtons per meter, a live load of 7.5 kilonewtons per meter, and the strength load combination that we're going to be investigating yields 17.5 kilonewtons per meter of load. So we're going to start using S-Line right away. So this is S-Line right here. It's used for concrete beam design and detailing, and it looks at the continuous length of a beam, so it considers things like stirrup spacing, bars, cutoffs, and whatnot. And it can have multiple bays with different section properties at each. However, for our example, we just have a simply supported 8 meter long bay, so I don't need to go into that much detail. So I'm going to change this. I'm going to go to Edit, General Information. And within this dialog here, I can specify not only my building codes and bar types, which I'm not going to worry about changing right now, but also the number of bays, which I'm going to set to equal 1. And then I'll press OK. And we can see here that we've now specified the number of bays that we have to 1. Any other changes that I want to make to the geometry can be made through the Edit Member Configuration dialog. Luckily for us, the 8,000 millimeter length matches what we need to use for our example. However, we're going to change this section size or shape to rectangular. And the depth of the section is going to be 500 millimeters. In terms of my actual boundary conditions, on the left-hand side, you can see that I have a column above and below, which I don't need. So I'm going to change this on the top here. I don't need to have any columns or any supports. Same thing on the right side as well. Set this to none. And below, I'm going to have pins on both sides. So I'm going to say a pin on the left side with the end condition being pin. And the same thing on the support below on the right. I'll say that's pin as well. And then I'll press OK. And I can see here that our geometry now represents what we wanted to represent compared to our hand calculations. We also need to consider our loading conditions. So if I go to Edit, Member Loads, here I can specify our loads that are applied to our model. In this situation here, I've got my dead loads of 5 kilonewtons per meter and my live loads of 7.5 kilonewtons per meter. So I can enter those. And I can see right now I'm looking at my dead load case, so it's got that magnitude shown there. And if I go to Edit, Load Cases and Combinations, I can also see that S-Line, when applicable, if we have more than one bay, will be able to automate the creation of pattern load cases for me and all my strength load combinations as well. So I've got my strength load combinations already set up and factored for me. And if I select one of them, I'll be able to see the magnitude of 17.5 kilonewtons per meter. Lastly, for this exercise, we're looking at a beam that has 5 20M bars within it. So I'm just going to go to Edit, Member Reinforcing. And within this rather large dialog that allows us to specify all sorts of different reinforcing conditions, I'm going to specify the longitudinal bottom middle bars, which will be where my maximum moment occurs. I'm going to specify it as having 5 20M bars. And we have different layers of bars that we can enter, and different types. Right now I have 2 20M bars in layer E1, which is at the bottom. We can see a little schematic here. And I have 2 25M bars within layer E2, which is basically just allowing us to specify different bar sizes in each layer. I'm going to set E2's quantity to 2, or 0 rather, and change the quantity of E1, the 20M bars, to 5. So I have 5 20M bars. You'll notice here I also have some longitudinal top left and right bars, which aren't really important for this exercise, so I'll just leave them in for now. And I'll press OK. At this stage, I'm going to go ahead and run an analysis and code check. So click Analyze and Code Check. And S-Line will ask us to start the analysis. Once it's completed, it's going to show us a detail of our reinforcing. So we can see the bars on the top on each side. And on the bottom, we have 520 M bars. We can also see our bar spacing at various locations. So I can see in the middle of my beam, I have 7 stirrups at 300 millimeter spacing. What's most important to me right now, though, is if I go to Results, and then I go to Moment Diagrams, I can see my moment diagram as well as the moment capacity envelope for my beam. That's what's indicated by these blue lines. And if I look at the worst case scenario for moment, it would be right in the middle of my beam. I can see that my positive moment capacity is 203.2 kilonewton meters. Compare that to my actual moment, my factored moment rather, that's 140 kilonewton meters. This is also reflected if I go to the results report and I click on bending moment. Here I can see that I have my MF, my factored moment, 140 kilonewton meters, and my moment that's being resisting, or my capacity rather, is 203.2 kilonewton meters. So we'll keep that number in the back of our head. And if we go back to the actual hand calculations that we were talking about earlier, we need to calculate our factored moment by hand. And I'm sure most of you would know how to do this. This is done with the following formula, where we equals 140 kilonewton meters. So this actually matches what we calculated in S-Line. And obviously, we want our moment capacity to exceed our factored moment. So using the CSA code for this example, we can calculate the stress block coefficients alpha 1, which equals 0.805, and beta 1, which equals 0.895. And from this, we can calculate the depth of our stress block, A, using the following formula, and we find that A equals 81.2 millimeters. And using this information, we can then calculate the neutral axis depth, C, to equal 90.7 millimeters. And finally, we can calculate our moment capacity, MR, using the following formula. And we find this to match the result we got from S-Line, which is 203.2 kilonewton meters. So here we've designed a concrete beam for Flexure using both S-Line and hand calculations, producing equivalent results.